Somewhere off a coral reef, a fish smaller than your hand is eating algae. Miles away, in open ocean, the largest turtle on Earth is struggling to survive. These two animals never touch. They never meet. But one may be quietly deciding the other's fate. In the next few minutes, you'll find out how. The leatherback sea turtle is unlike any other turtle alive. It has no hard shell, just leathery skin over cartilage. It can grow past 6 feet long and dive deeper than almost any marine reptile on the planet. It has survived since the age of dinosaurs. And yet today, it's disappearing faster than almost any species like it. Multiple leatherback populations across the Pacific have declined by over 90% in recent decades, according to long-term nesting surveys. That's not a small dip. That's a population in collapse. Scientists have spent years asking why, and the answers keep pointing towards something most people would never expect to matter this much. Most people assume sea turtles are threatened by fishing nets, plastic pollution, or poaching alone. Those threats are real. But researchers studying leatherback decline kept finding gaps those factors couldn't fully explain. Something else was affecting their food supply, their migration success, their nesting outcomes, and that search led straight back to coral reefs. Here's the part that confuses people first. Leatherbacks aren't reef animals. They spend most of their lives in open water, diving for jellyfish, far from coral. So why would a reef fish thousands of miles from a leatherback's usual habitat matter at all? The answer isn't direct. It's a chain reaction, one link at a time. Surgeonfish are mid-sized reef fish, named for the razor-sharp spines near their tails. They're herbivores, spending nearly all day grazing on algae growing across coral surfaces. On their own, they don't look important. But on healthy reefs, they perform one of the most critical jobs in the entire ecosystem, and they do it constantly. Coral reefs are in a constant battle against algae. Left unchecked, algae grows over coral surfaces, blocking sunlight and smothering the coral polyps underneath. Once algae takes over, coral can't recover easily. This isn't a minor cosmetic issue. It's a fight for the reef's basic survival, happening every single day, all across the reef. Surgeonfish graze algae down constantly, preventing it from overwhelming coral. Research on herbivorous reef fish confirms that grazing pressure from species like surgeonfish directly affects how much algae accumulates and how well coral can recover after disturbances like bleaching events. Remove enough of these grazers, and reefs shift toward algae-dominated, degraded systems. Overfishing has stripped surgeonfish and other herbivorous fish from reefs across the world. Studies from the Caribbean and Indo-Pacific show that reefs losing their grazers experience faster algae overgrowth and slower coral recovery after bleaching. A reef without enough surgeonfish isn't just less colorful. It becomes structurally weaker, less diverse, and less alive. A degraded reef doesn't just affect coral and fish. It changes the entire surrounding marine food web, including the invertebrate populations living around reef edges and open water nearby. And leatherback turtles depend heavily on one very specific part of that food web, something soft, something drifting, something most people overlook completely. Leatherback turtles eat almost nothing but jellyfish, consuming massive quantities to sustain their enormous size. An adult leatherback can eat its own body weight in jellyfish in a single day, according to marine biologists, tracking their feeding behavior. Their entire life strategy is built around finding enough jellyfish, consistently, across thousands of miles of ocean. Coral reef ecosystems influence nearby jellyfish populations in complex ways, through changes in water chemistry, competing species, and nutrient cycling tied to reef health. Degraded reefs, overloaded with algae, alter local ecological balance in ways that can affect jellyfish abundance and distribution near reef zones that leatherbacks pass through during migration. It's important to be precise about this relationship. This isn't a simple, direct chain where surgeonfish alone determine jellyfish numbers. It's part of a much larger, interconnected reef ecosystem. Surgeonfish are one significant piece of that system, not the sole cause. Overstating that connection would misrepresent what the actual research shows. So calling this survival impossible without surgeonfish isn't about one fish controlling one turtle's fate directly. It's about an entire reef ecosystem, one where surgeonfish play an essential structural role, shaping conditions that ripple outward toward the open water food sources leatherbacks depend on for their long migratory journeys across ocean basins. Leatherbacks travel some of the longest migration routes of any marine reptile, moving between nesting beaches and distant feeding grounds across entire ocean basins. Along these routes, they pass near reef systems and their surrounding waters repeatedly. Changes in those ecosystems, compounding over a multi-thousand-mile journey, can meaningfully affect their feeding success. Marine biologists increasingly view reef health as an indicator-species relationship, a warning sign for wider ocean conditions. When reef grazers like surgeonfish decline, it signals stress moving through the entire marine system, stress that eventually reaches species far outside the reef itself, including deep-diving, open ocean travelers like the leatherback turtle. Recent studies tracking leatherback nesting success alongside regional reef health data revealed a correlation stronger than anyone initially predicted. In areas where reef degradation was most severe, nesting failure rates and hatchling survival numbers showed troubling parallel declines. That correlation raised an uncomfortable question researchers couldn't ignore any longer, because what that data suggested wasn't just an indirect ripple effect anymore. It hinted at something closer to a genuine dependency, one running quietly beneath the surface of two ecosystems everyone assumed were separate. And once researchers followed that thread further, the real scope of the connection became impossible to dismiss. Researchers began mapping reef degradation zones against known leatherback migratory corridors, comparing decades of satellite tracking data with reef survey records. The overlap wasn't small. Many of the most heavily used leatherback feeding corridors ran directly through regions where reef grazer populations, including surgeonfish, had collapsed most severely in recent decades. Leatherbacks don't feed randomly across the ocean. They follow current systems and productivity zones that reliably concentrate jellyfish, often near reef-influenced coastal waters. When those specific zones degrade, the turtles don't have unlimited alternatives. Their entire feeding strategy depends on a limited number of predictable, productive corridors staying intact. Here's the fuller chain now coming into focus. Fewer surgeonfish leads to more algae. More algae leads to weaker, less resilient coral reefs. Weaker reefs alter local marine chemistry and invertebrate populations. And those shifts ripple into the jellyfish availability leatherbacks rely on precisely where their migration routes concentrate feeding activity. Marine ecologists increasingly describe this as a documented ecological cascade, not a hypothetical chain of coincidences. Cascading effects, where removing one species trigger changes rippling through multiple trophic levels, are well established in reef science. What's newer is tracing that cascade far enough to implicate a species as distant as the leatherback turtle. For years, turtle conservation and reef conservation operated as separate scientific fields, studied by different researchers, funded through different programs. Nobody was systematically comparing surgeonfish population data against leatherback nesting success. It took cross-disciplinary collaboration, marine ecologists and reptile biologists working together, to finally see this connection clearly. This creates a serious problem for conservation strategy. Protecting leatherback nesting beaches alone, while ignoring reef health thousands of miles away, may not be enough to reverse population decline. If the underlying food chain is compromised at its source, beach protection addresses only one piece of a much larger, interconnected survival puzzle. This reframes what protecting a coral reef actually accomplishes. Preserving surgeonfish populations through fishing regulations doesn't just protect coral cover and reef biodiversity. It may be indirectly protecting the food availability of a critically declining sea turtle species that most people would never think to connect to a reef fish at all. Surgeonfish face heavy fishing pressure across many reef regions, both for food markets and the aquarium trade. Removing large numbers of grazers accelerates algae overgrowth far faster than reefs can naturally recover from. Every unsustainable harvest of surgeonfish adds pressure to a chain reaction, extending far beyond the reef itself. Rising ocean temperatures and repeated coral bleaching events already stress reef systems independently. Without enough surgeonfish grazing away algae during recovery periods after bleaching, reefs struggle to bounce back at all. Climate stress and grazer loss compound each other, accelerating reef decline faster than either pressure would cause alone. It would be easier if this story had one clear villain, one single fixable cause. It doesn't. This is multiple stressors: overfishing, warming oceans, habitat loss, interacting simultaneously across two ecosystems that most people never imagined were connected. That complexity is exactly why leatherback decline has been so difficult to reverse. It's worth repeating clearly, because this gets misunderstood often. Surgeonfish are not a direct food source for leatherback turtles. Leatherbacks don't eat surgeonfish. The relationship is ecological and indirect, running through reef health, algae control, and downstream effects on invertebrate populations, not through any direct predator-prey interaction between the two species. Even without direct interaction, researchers argue this relationship qualifies as genuinely critical because removing surgeonfish contributes measurably to reef collapse, and reef collapse measurably correlates with degraded conditions along leatherback feeding corridors. Indirect doesn't mean unimportant. In interconnected ecosystems, indirect relationships can carry consequences just as severe as direct ones. Scientists are now pushing for longer-term, more granular studies, tracking specific reef sites, specific surgeonfish population changes, and specific leatherback feeding success over extended periods. The goal is establishing clearer causal strength behind this correlation, moving from a compelling pattern toward a fully quantified, defensible ecological mechanism accepted across the field. If this connection holds up under continued research, conservation strategy may need a serious shift. Protecting leatherback turtles could require protecting reef grazer populations thousands of miles from any nesting beach. Ocean conservation, this case suggests, cannot keep treating distant ecosystems as isolated problems with isolated independent solutions. So why can't the leatherback sea turtle survive without surgeonfish? Not because of any direct bond between the two animals, because a small algae-eating fish helps hold an entire reef ecosystem together, one whose health quietly shapes the food supply an ancient ocean giant depends on across thousands of miles of migration. This story is bigger than one fish and one turtle. It's a reminder that ocean ecosystems function as single, interconnected systems, not isolated compartments. Removing one small piece, one grazing fish on a distant reef, can ripple outward for years before its true cost becomes visible in a species nobody thought to connect it to. So the next time someone tells you a small reef fish doesn't matter, remember this chain: algae, coral, jellyfish, and a turtle that has survived since the age of dinosaurs. Now caught in a decline, scientists are still working to fully understand. If uncovering hidden connections like this fascinates you, subscribe now. The next investigation goes even further beneath the surface.